Okay, so everybody is welcome. This is Physics 1 class, and this will be about mechanics. The subject of this will be mechanics. So first, let's see just what the introduction is all about. In the first place, we are talking about that physics is somewhat different of math in terms that physics have real quantities, not just abstract numbers. In here, we have also a number and the measuring unit, and they are multiplied together. So the physical quantity consists of partly a number, which is the measuring number, and the unit. And these two are multiplied together. In addition, in here, we have a concept which is called accuracy. The accuracy of the measuring number is always an important point, that these are not just an infinitely accurate number, but in the most cases, it is having an error, and this error has to be taken into account in all cases. We have to know how accurate the number what we are saying. And I have here written an example. I'm just looking for this with my eyes. So yes, because of this 1,000, so 1,500 meter and 1.5 kilometer written down are not equivalent in terms of accuracy, because the first one has an accuracy of 1 meter, and another one has an accuracy of 100 meter. So the absolute errors in one case 1 meter, in another case 100 meter. The relative error, if we are comparing this absolute error to the face value of the quantity, so we divide it with the original value, and therefore it is giving us a percentage, how accurate the number is, how many digits this one is accurate. So in the last word is that in physics the accuracy is important, and we have to be sure that if we divide a number with another one, we don't write down all the 6 or 7 or more digits from the calculator. If we divide it with 3 by 7, we get a very long number, but we don't need to write it down. We must not write it down, because the result may not be more accurate than the numbers we started from. Therefore, an intelligent solution is cut down the number of decimal points where the accuracy ends, and therefore we are not having those fake numbers at the end, which just shows that we are not able to find out how accurate the number is what we are using. Okay, so let's go further on. First, we are talking about the kinematics of the particle. Particle is a little object, and it's a physical model, which means that the extension of the object is far smaller than the experiment around it. Therefore, we can consider it like a point. So therefore, if we are talking about a particle, we just consider it as it was a particle in terms of physics, a mathematical point. We don't care about its extension. So it's a point-like mass which lacks any extension. This is the model we are using, and we will discuss the kinematics of the particle. Kinematics is just the description of motion without any respect to the cause of the motion. So in here, we are not talking about any mass, any forces. This will follow later. In here, we have just quantities that the coordinates, the ijk coordinates in the Cartesian system, and the time. And these two will describe the position of the particle, and the related quantities will be derived from these parameters, but we are not going to make any further physical conclusions of this. From this point of view, all kinds of reference frames are equivalent, because if we have no mass, if we have no particles, if we have no forces, we don't need to deal with the question what kind of coordinate system we are using. This will be important later in the dynamics. So in this point, any coordinate system is good, just like if we put our coordinate system into a roller coaster, that is still good. Or if whatever it is, we don't need to deal with that. So let's just have a look. We have an arbitrary coordinate system, and we want to describe the motion. The first and the easiest motion which we are dealing with is the rectilinear motion. The rectilinear motion is a linear, means going on a straight line, linear on a line, and the rectilinear motion, it's a motion which is going to happen in a straight line. It doesn't mean anymore that it is only an xt function, where x is the position, because we choose a coordinate system, an x coordinate, which is parallel with the motion of the particle. The velocity of this particle is the first derivative of the position function. The everyday concept of speed is the magnitude of the velocity vector. Let me emphasize that in physics, the velocity is a vector, the speed is the magnitude of the vector, is just a number, right? Therefore, the speed is always a non-negative number, while the velocity can be a negative number in a rectilinear motion, because can be shown either from left to right or right to left. Let's see why it is. I hope you have learned infinitesimal calculus at high school, but let me just try to explain what it happens. We have a small displacement in x position, and relative to that, a small displacement in time, a small elapsed time. And if we divide these two, we recover an average velocity for that little dt time, delta t time. But this one is not an instantaneous value, but it's characteristic to that finite delta t interval. In order to have a instantaneous velocity value, we have to make a mathematical operation which is called the limit. And in the limit or limes operation, the delta t goes to 0, and this one is going to go to the dx over dt. It's the notation, the d is the limit value of the delta, which is infinitely, in quotes I'm saying. So in math, people don't like to say that infinitely small. They are not infinitely. So it's the limit value of the limes delta x over delta t value. This is the dx over dt, and this is called the velocity of the rectilinear motion measured in meters per second. The opposite direction operation recovers the position from the velocity. Here, let me explain that. For those who did not learn, it would be a difficult time to understand it so suddenly, but let me explain that. If we have a velocity time function, and we have this, and we want to find out where the particle is, then we have to do that. We have to make an operation that the velocity is subdivided, the time is subdivided to small intervals, and each of those are multiplied with the corresponding representative velocity value, and then those are added together. And then finally, the subdivision goes to infinite fine, and this formula here means an integration, the integral, definite integral from 0 to t. And in here, some primes means that this prime and that t is not the same, because the t prime dt prime is the integration variable, And now the t is the limit value of the integration, and that will give us back the original xt value. So this is back and forth operation, the differentiation and the integration. But I hope this is known for most people or almost everyone, because we will be using these things frequently. So the acceleration of particle is another operation, one more differentiation. So the derivative of the velocity versus time function is the acceleration. What we do, we watch how much the velocity variation was and divide it with the elapsed time. And then we push this to the limit by delta t goes to 0. And this will be equal with the first derivative of the velocity and the second derivative of the position. And that will be the acceleration. And that will be mass over secondum square. The opposite direction operation recovers the very similar way as it was. From the acceleration, we recover the velocity by having the initial value and integrating from 0 to an actual t value, the acceleration, and t prime again is the integration variable, which is different from the t, because t is the end of the integration and t prime is the integration variable according which this integration or summation is going on. Okay, I hope this was clear. Now let's check the next point, uniform rectilinear motion. So far it was a general rectilinear motion. This was giving us the general formulas. Now these formulas will be actual formulas for some specific types. This one is the uniform rectilinear motion, and here the acceleration of the particle is 0, is a special type of motion. The above formulas, which I have shown it to you now, transform to the following special cases. This one, acceleration is 0, velocity is constant, and the position is this. If we watch, we can carry out this in here. If we have a 0 acceleration, then this is giving us 0 here, and the velocity will be constant. And if we integrate this one, constant integrated will give us this slopey function, right? So that is the easiest, practically easiest motion, which is going to happen in a straight line and with very constant velocity. It's an absolutely constant velocity in the straight direction. That is the uniform rectilinear motion. The next point is when the acceleration is not 0 as it was, but it is a constant acceleration. So in here the acceleration will be constant. And if we integrate that according to those formula, the integrated value of constant is a linear slope, v nu plus at, and integrated of the linear slope is a parabolic slope, is a quadratic formula, is this one. A typical example is the free fall when something is dropping, falling down, then this is the case. Now, let's check. The harmonic oscillatory motion. A harmonic oscillatory motion will be treated also later in this lecture, but in here I cannot omit this from the description of motion because it's very important of that. But later in this chapter, in the second half of the semester, it will be discussed again. But let me say that. So the harmonic oscillatory motion, it can be derived as the projected motion of a circular, uniform circular motion. That is a harmonic oscillator. The two coordinates, these are, if it is going to go around omega t plus phi, omega is the angular velocity, and this is going, it is going around uniforms, angular velocity, and this is projected to the vertical and horizontal axis. So x and y will be coming out, and the uniform circular motion is a projected motion, and here is we choose the x1, the cosine, because the cosine will be good for other later purposes. Cosine is good because when omega goes to 0, and we are watching what happens by changing the frequency, if we chose another one, that would be a problem because the sine is vanishing when the cosine, when the omega is going to, when the argumentum is vanishing, then the sine is vanishing, and therefore the cosine is the good choice for discussion. So displacement oscillator motion called excursion, the excursion, and this one is called the phase in the parentheses. And now if we go on, the velocity of that is the derivative as before, as we know, the cosine derivative is going up to this, and it is multiplied with the omega, which is coming out from the argumentum as internal derivative. The multiplier trigonometric is called velocity. The multiplier of the trigonometric term is called A omega, is called the V max, the maximum velocity, velocity amplitude. The acceleration is the derivative of the velocity. Again, here comes again the derivation. We differentiate this one more omega is coming over here, and it's going to under the square. And now we find out that this one, A omega square cosine, and now we substitute A cosine the xt. So we will have here the acceleration will be negative omega square opposite to the displacement. According to the acceleration, always positive phase position relative to the displacement. So the acceleration points always opposite direction as the acceleration. The acceleration and the displacement are opposite direction. That is, the minutes is shown up here. Okay, that was about the circular motion description. Now comes the curvilinear motion. So far, rectilinear motion was everything, because this is always also happening in the straight line. So the harmonic oscillatory motion is in a straight line motion. But curvilinear motion is a motion which is not a straight line, but whatever arbitrary shape. And therefore, it can be written with a vector scalar function. This one is the vector, here is the scalar, and this is RT function, vector scalar function. The velocity of the particle, first derivative of the position function, this one, if we differentiate that, that means the differentiation is a linear operation, so we can make them separately to the coordinates by keeping the ijk multipliers next to them. Therefore, the velocity will be showing up like this. Similarly, here is an important point. The velocity vector is tangential to the trajectory of the particle at all times. So the velocity is always tangential to the trajectory. The vector of acceleration is a derivative of the velocity vector. The vector of acceleration can be composed of parallel and normal direction relative to the velocity. So if we watch that, we differentiate this one, all these second derivatives will show up, but in here, the acceleration can be decomposed with a parallel and with a normal direction acceleration, which is called the centripetal acceleration. This is the normal. This is the centripetal or normal direction, and this will be the tangential direction acceleration. So these two combine give us the total acceleration. The parallel component of acceleration called the tangential, and this is coming because this is the result of variation of the velocity magnitude. So if we drive a car on that road, then we will have tangential acceleration if we push the gas or if we slam on the brake. Then the acceleration will, the tangential acceleration will be parallel with the velocity if we push the gas, and will be opposite with the velocity when we push the brake. But in all cases, the centripetal or normal direction acceleration will point to the center of the curvature. So let's say maybe here. So if this is approximated to the circle, then the center of the circle is the place where the normal direction acceleration, so the centripetal acceleration, points to. Okay, this is okay. That's what I had said. And here is the example of with the car. That's what I had already explained. Here comes the projectile motion. Projectile motion is a projectile, or either a projectile of an artillery gun or a simple stone which somebody throws away. This is all described with the projectile motion. Projectile is a mass particle without extension, so it's a particle, mass particle, and the model contains some simplifications, such as gravity field is homogeneous, rotation of the planet Earth is ignored, and the drag due to air friction will be disregarded also. So it's a fairly similar, a fairly simplified model. We have the homogeneous gravity, so we don't need to care about the rotation of the Earth and the drag of the air and such things. This is a very simple approach, and it's usable for simple environments. So it was just throwing a stone, but for having a long range shot with a gun, or even a long kick with the soccer ball is not good for that, because they are so much different. This model is very crude and rough, so what we have here is not a very good approximation of the real world, but in the simple cases this will work. Let's check this model now. We have the coordinate system in the center. We have the point where this particle is started from, and this is fired with the velocity v null, and the angle relative to the horizontal is the alpha, and it is flying on a trajectory like parabola, and we want to find out the h, the height, and the d, which is the flight distance, how far it went. So let's check this out. The projectile is fired from here. The motion is getting, so we will be working out the vector scalar function of the flight. First, we know how much the velocities are. We have here a Vx velocity, which is a constant velocity, because in this direction there is no force. Force is a vertical force. So the horizontal direction, in horizontal direction, there is no any force, which means that the Vx is a V null times the cosine alpha is constant all the way. The Vy, on the other hand, which is the vertical velocity, is composed of two things. One of them is a homogeneous constant velocity, but it has a superimposed free fall term, which is because the particle is subjected to the gravity, so it is falling down. So it is composed of a uniform traveling to the right and a free fall. The corresponding position coordinates are integrated from the formulas with zero initial condition. So the xt is the integral of Vx, t dt, so it is primed, which means that they are just the integration variables. These are V nu t times cosine alpha. Cosine alpha is a constant, and the V null is a constant. The integrated constant is the V null times t. The y is the integrated value of this one. Integrated value, if we put it in here, we see that we have this one, an integrated V nu t sine alpha, and the gt integrated g over 2t square. So these are the vector scalar function of t, x and y are the coordinates of the vector, and this is this one, and this one is a t function. So ultimately, this is the vector scalar function. Two critical parameters are needed to find out. This is what I said, the h and the d parameters. First, the rise time should be calculated. The rise time is the duration from the start to finish of the vertical. The rise time is the duration from the start to the vanishing of the vertical velocity of the component. In other words, from the start to the top. Because in here, the vertical component vanishes. Vertical component is turning from the up to down, and here the vertical component is 0, and it's having only a horizontal component. So ultimately, when we consider this, this one as equals with 0, we put it, make it equal with 0, we can express the rise time. We can express, not this, sorry, this one, I was wrong, this one. The velocity is vanishing, not, I made a mistake. So this one here equals 0. From here, V nu sine alpha over g is the rise time, okay? And now with rise time is now substituted to the y coordinate, to this one, and we get how high will be it's on the top. Is the t equals the rise time, so we put this one, V nu t sine g over 2, and we have here the rise time instead of the t. So now we can take this and write into there, into here, substitute this one, and if you now multiply this V nu goes to the square, sine and sine goes to the square, g is what it is, what it was there, and the negative g over 2, and this one is put to the second power. Exactly. Now, if we add them together, we get an easy result that V nu square sine alpha over 2g, this is the highest value in the trajectory. The rise and the fall part of the motion are equal in duration due to symmetry of the motion. As I wrote it here, because of this, the total flight time of the motion is twice longer than the rise time alone. The horizontal flight distance can be calculated from the x-coordinate at double rise time moment. So here the d and the x is, which is a d, where d is an x value at 2 rise time moment. So we have to take the x, which is this one, and in here we have to write 2 times the rise time, v naught t rise time, v naught t rise time. This is the rise time. This one is the rise time, v naught c2g, v naught c2g, and 2, it's 2 times of that. And also in here, in the second part, this one g over 2 times, and this one is on the square. And ultimately, we have this one here, the d, the distance. The flight distance is the product of sine and cosine multiplied 2 times. And we can immediately find out that this is the sine 2 alpha function. So we get a simple result, v naught square over 2. V naught square. No. Here we have, finally I found an error, gosh. Because it's not 2 but g here, it's an error. I was sure there was no error, and immediately I found an error. Sorry about that. So this is v naught square over g and not 2. Okay. This is clear. This clearly shows that the projectile flies the furthest if the angle is shot is 45 degrees, because when this one is 1, it is the furthest, and that is the 45-degree position is the longest. So please correct this 2 for the G, because as we see it here, this is good, but this is wrong here, because when I made this, I just, because of any reason, I did not copy it correctly. Okay. Now, this was the projectile motion, which is a special motion when homogeneous gravity is affecting a particle. Now here comes another one, and this one, the circular motion. Circular motion is a very frequent thing. In circular motion, the particle moves in a circular plane trajectory. To describe the position of the particle, polar coordinates are used. The origin of the polar coordinate system is the center of the motion. So in other words, a circular coordinate. The only variable parameter is the angular position, since the radial position is constant. We are always the same distance, but we just go around, and only the angle is under question. The derivative of the angular position is the angular velocity. So the angle is similarly the little variation divided with the time, and then comes the limit, the very same story as it was earlier. We have here a derivative of the position, angular position, and this is the angular velocity. Up to this moment, looks as angular velocity were a number, but it is not the case, because we want to extend the definition of the omega vector, the angular velocity vector, because the rotation is not just a number associated, but it's also associated with an axis. So it's worth introducing an angular velocity which is showing us not just how fast it is spinning, but also shows what axis it is spinning around. Therefore, we introduce a velocity vector, an omega vector, which is in here in a bold print, is an omega, and the definition is the following. The magnitude of the omega vector is what we have explained here when it was thought to be a number only. But if we want this to be a vector and we want to contain the information on what axis it is around, the direction of the is perpendicular, in other words, normal to the plane of the rotation, and the direction results as a right-hand screw rotation. Everybody has the feeling in the hand that if we want to put a screw into a wood or into a wall, has to turn in the parallel rotation with the parallel direction with the clock. So the clockwise rotation, and if you make a clockwise rotation, this clockwise rotation goes into the wall, so ahead. If it is turning to the counterclockwise direction, it is coming backward. So ultimately, the definition is that the omega vector is the magnitude, is the speed, how fast it is spinning, as it is written here, and the direction is defined by the plane of the rotation, that taking the rotation as a direction and taking the right-hand screw, where the right-hand screw travels, that is the direction of the omega vector. If it is a clockwise rotation, that is pointing ahead. When it is a counterclockwise, it's coming back. So that is the definition, and it's a very useful counterclockwise rotation will always result omega vector pointing upward from the plane, away from the plane. That is a very useful definition because it is making us possible to use it without so many words and verbal explanation. We will be able to use this omega vector for having the results in mechanics, just because, as we know, we will have here the result as a vector, and we will be able to find out not just how fast it is, but what direction it is. And the first example of this is the velocity of the omega. So if we have a particle which is having an omega angular velocity, then the velocity of the particle is omega cross r, which means the omega vector and the r position vector are cross-produced in a mathematical way. As we know, let's take the first factor omega and turn to the r, the second parameter, the second component, and this turning will define the rotation, and this will define the velocity. Omega cross r will be the velocity of the particle. The velocity vector is sometimes called circumferential velocity, but it's not necessary to say because all the velocities are circumferentials. The cross product of vectors in mathematics has clear definition by turning the first vector as what I had said, first into the second, and the direction defines the direction of the cross product. Now we want to use this vector product in later use, And we want to combine it with the differentiation by time mostly. And because of this, we have to declare some mathematical theorems that we should be able to use it by an algebra by combining them with the derivation. So let's check this out. If we have a cross product, we can differentiate it in the same way as it was a simple product function, because take the first derivative, multiply with the second, and take the first one, multiply with the second derivative. And similarly, in case of dot product, which is giving us a number, a scalar, this product here, and this, take the first one, differentiate it, and take the second, and so on. And also with the scalar multiplier, this is the very same way. So these formulas make it possible to use the same differentiation rules among vector products, just like among ordinary product functions. And this is true both cross product and product operations. The proof of these rules are quite straightforward. The vector should be written by components, and the match, the two sides should be verified. So we just have to take some vectors, write them in coordinates, carry out the cross product with the determinant, and make the differentiation and check that this is going out. And in fact, it is working. We now don't make these proofs, but I felt obligated to at least declare these, because in some lectures they consider it as it was obvious and they don't even mention it. And after that, they are using these rules, which we will be using without any further, and they pretend as it was obvious. But this at least should be clearly stated that this is in fact good and is working. Now, omega vector is a powerful means. Let's check this out. This way, the acceleration vector of a particle can be determined by the relative ease. So easily, not so many words and drawings and stuff. We can use it, a very, very useful, strong means, by taking the omega cross r as the velocity and take the derivative. And this is a cross product, and according to the rules above, we have to differentiate this one and differentiate this one. The derivative is omega is called the angular acceleration, is the beta vector. This is the derivative of the omega. This can either just, if the omega is also changing in direction, this b vector is also pointing how the axis of the omega is changing, but also shows how intensive is the magnitude change. So it is a full derivative of the omega. And another one, dr over dt. The dr over dt is a velocity, and the velocity again omega cross r, as we had already stated up here, the velocity omega cross r. So we just substitute it in here, and we recover that the acceleration of a rectilinear motion particle is it is a circular motion, but it's in fact a rectilinear motion, curvilinear motion, sorry. Then the beta cross r and omega cross r. Our formula consists of two major terms. The first term is called the tangential acceleration, bit one. This one here, the tangential acceleration. In case the particle motion is parallel or opposite to the velocity, and it is consequence of speeding or slowing down, this one. As explained earlier in part of this chapter, the second term is called the centripetal acceleration, omega cross omega cross. This component points toward the center of the rotation. The centripetal acceleration is the consequence of the direction of variation of the velocity vector. The magnitude of these components can readily be expressed. So that one here, omega tangential acceleration, is the magnitude of this one, which is in a circular motion. It's simply the product. And this one here is omega cross r. If we consider the magnitude, omega omega cross r is r omega square, or if we substitute the velocity into here, this v square over r. There are two special kinds of circular motion, the uniform and the uniformly accelerating circular motion. So far it was the general circular motion. Let's check the uniform circular motion. The circular motion of uniform, in here angular velocity is constant. Angular velocity is constant. The angle of rotation can be expressed so easily, simply. And angular acceleration is 0. No tangential acceleration will show up. So however, there will be constant intensity centripetal acceleration, and this one is that. So these formulas appear when the beta is 0, this is gone, and the v square over r omega square is what we have still there. Now comes the next point, uniformly accelerating circular motion. In here, the angular acceleration is constant. Corresponding formulas are analogous to the uniformly accelerating rectilinear motion explained earlier in this chapter very well. So this is the omega, which is the linear function of the time, and is integrated by time. It is the quadratic formula of the position. The intensity of the tangential acceleration is constant. The tangential acceleration is constant, so it is going faster and faster, and parallel with the velocity vector. The intensity of centripetal component is quadratic dependence of time, so r omega square, and omega is this one is substituted here, and omega is increasing fast. And this one are normal to each other. So if one wants to find out how much the total acceleration is, this one and this one has to be added together as the Pythagoras theorem. So square on this plus square on this under the square root will give us the total acceleration in this motion. But I didn't want to complicate too much the formulas. Now let's check the final of this chapter, the areal velocity. Areal velocity is a velocity which will be used extensively in the planetary motion. When the objects go around the sun, the Earth and the other solar object. So let's consider a particle traveling on this trajectory. This is the trajectory. If one draws a line between the origin of the coordinate system and the particle, this line is called the radius vector. This is the radius vector. The vector of the area velocity is the ratio of the area swept by the radius vector over time. So in other words, how fast this swept area changes. The crosshatched triangle of the figure above is the magnitude of the infinitesimal variation dA. It's a very, very small, very, very narrow little triangle-like object, or yes, it's like a triangle of the swept area vector. So the dA is vector is the r cross dr, because this is a triangle, and the triangle has an area definition that this vector and that vector multiplied together and multiply with the sine of the angle, and this is exactly the magnitude of this is the area of this. But in addition, this area vector is not just a number, but it's a vector, and this has the definition that this one and this one over 2, I forgot to say, so over 2, this one and this one multiplied together over 2 is giving us this area, this very narrow area. And if we say that this is if we want this to be a vector, we consider them two vectors and not just two numbers. Therefore, the area will be showing up as a vector here, which is pointing out because the R and the dr, R should be turned to dr. It's a right-hand screw rotation, goes into the sheet of the paper. So this is the dA area here. On the other hand, the dA is v dt because dr is the v dt. This one little dr is the v times dt. So after this, we can formula this, that dt comes over to this side, and that will be the dA over dt. That will be the areal velocity, because this was just the cross product, which is an area, but areal velocity is divided with time. It is 1/2 r cross v. So the position and the velocity cross produced is giving us the areal velocity, the swept area over time. And this is 1/2 r cross v. And this will be used later in this book in the planetary motion of the particles of the planets. So this first chapter, this was the first chapter of the kinematics, and now we finish it for a while. Later we continue it with the dynamics. Thank you.